Okay, I'm the next speaker, Bill Gray. My talk, I agree with most of the things that Bill says, but I have two factors to talk about. One is CO2 cannot warm the globe much if it doubles or it quadruples. And whatever climate changes we've seen are primarily due to the ocean. I don't believe much in solar effects. I don't believe in aerosol changes too much. I don't believe in cosmic rays and various other things. So I've got a slide talk here. There is no scientific justification for CO2 global warming hypothesis. Now, the problem has started, as I view it for many years, with a Charney hypothesis, or the National Academy report of 1979, known as the Charney report, where they assumed that if CO2 doubles, you're going to get between 1.5 and 4.5 degrees centigrade change of the surface global temperature, or 3 degrees. There's no way that can happen. The way they got it was they assumed, okay, you double CO2, the net radiation effect of that is to warm the atmosphere 1 degree. But that's not really true. It'll only warm about half because the ocean evaporation will take the other half. So already, this is not very valid. Then they assume, and this is the crux of the thing, they assume that the warming will take place, that the relative humidity of the atmosphere will remain quasi-constant. That's the drawback to the whole global warming idea as I see it. That's not such a bad concept in middle and lower troposphere, but it doesn't work in the upper troposphere because cumulonimbus clouds go through the whole troposphere and their rainfall efficiency is very high and their subsidence warms tremendously, but mainly drying. It dries tremendously, lowers the emission level to a warmer temperature, and more radiation is fluxed out the top. So now you know all the climate models. They all show with a doubling of CO2 that you warm the upper troposphere of the tropics a great deal. Hansen even had 7 degrees warming in his model. Now we're about halfway through to a doubling of CO2 now if you assume that the effects of the CO2 go up as a log of the concentration. So we're roughly half of this, and we've seen none of this in the upper troposphere. A little bit of warming, but hardly nothing. So the hypothesis of all the models is failing very badly. Now the problem rests with this. You see, the models say that because the clouds are saturated, you get more clouds. The saturated vapor goes out at the sides and moistens the upper troposphere. And that moistening blocks IR loss to space and reduces the amount of IR loss to space. Whereas reality, as I see it, and all the data we've been assembling, I have some colleagues here, and you have these deep cumulonimbus that go through, and the subsidence on the side dries so much because the saturation vapor pressure in the upper part of the troposphere is, you have such a great gradient of it from the top to the bottom, that air starting out here coming down to, say, 300 millibars or 10 kilometers only has a relative humidity 20–30% or so. So that's the cruise. Here's what it is. You have a deep cumulonimbus from 300 millibars height or 10 kilometers. This air goes down. It arrives here at only 1/16 the amount of vapor, of saturated vapor pressure here that it started out here. So it's the upper troposphere does not moisten as everybody thinks it does as CO2 goes up and rain gets greater. You'll get more rain, which you will with the CO2. My estimate is about 3% more rain when CO2 doubles. But you'll get more cumulonimbus clouds, and those cumulonimbus will dry the upper troposphere, lower the emission level, and let more IR loss to space. So we also have with the models a grid point problem. You see the models, if you have a model, between grid points, you may have a mean upward vertical motion there. You've got to have more moisture here. But the real clouds are on a much smaller scale. The up and down drafts between grid points can make you have much more vertical motion at reduced areas and subsidence here, and this grid point can have a much lower vapor and more radiation to space. Now, Jim Hansen, in his testimony to Congress in June of '88, assumed there was tremendous moisture in the upper troposphere. This is what he did. This is one of his early models. He had 50% water vapor extra in the upper troposphere when it should have gone down. He made the relative humidity not go down as our observations show, but go up. So of course he got warming. And we knew it then. We all said it's a water vapor feedback loop, but nobody listened to us guys that have been in the tropics, working with storms and all the tropical experiments we went on in all these years. We're forgotten. We're isolated, put out in the side. The IPP never contacted me. So now what will really happen is there's no doubt that doubling CO2 is going to reduce this IR loss to space by about 3.7 watts, about 1.2 or 3% of what the incoming solar and the outgoing IR and albedo is. So this will filter down to the surface, and the surface must balance this 3.7 due to the doubling of CO2. To do that, it doesn't have to warm much. 0.2, 0.3 degrees, that's all to increase IR, sensible heat, evaporation will go up 3% to get our 3.7. This will go in with the extra CB clouds, the vapor in the upper troposphere goes down and the 3.7 goes out. There won't be much happening when you double CO2. Here's what the models say. Here's what I estimate. The radiation effect won't be 1, it'll be about half. With the oceans doing the other, the feedback is negative, and we'll see probably at a doubling of CO2, 0.3, 1/10 as much as most of the models say. So we don't have to worry much about CO2. Even when it quadruples, we don't have to worry much. It's, and you know, crops grow better, we have more rainfall, that'll be better, the globe's slightly warmer, that'll be better. So what's the cause of all this? I agree with Bill Kennymund here. It's the main driver is climate change, is the deep ocean circulation changes driven by salinity variations. And this is sort of a look. This is the South Pole, the North Pole. Here's the ocean. You know the mean temperature of the ocean? It's only about 3 degrees C. It's cold. Most of the ocean is very cold. And we have this MOC, meridional overturning circulation, where we have subsidence near the poles, upwelling more in the southern hemisphere as Bill Kinneman talked about, and this was quite different in the Cretaceous period where due to a lot of effects, swampy areas and salinity variations, you tended to have it go the other way, and the poles were much warmer. So what this happens is the stronger this circulation is, the more you upwell cold water into the warm areas, and the global rainfall is more. So you have more global rainfall, more evaporation, and more cooling. When this is weaker than normal, you have the opposite. So you've all seen the thermohaline, or the AMO, has different strength levels. We have surrounding Antarctica subsidence here. Here's another thing, the water sinking here, coming up in this broad area here. When it's faster than normal, here's sort of a mean case. You have this circulation. The steady state thing is the solar balance is what comes out and what rains. When this is stronger, you cool the globe. When it's weaker, you warm the globe. And the MOC brings all these changes about. I won't have time to talk about them. Here's the way the globe has warmed since about 1880. We've had cooling periods, warming, cooling, warming, and now a period of maybe slight cooling or not warming. And all this sort of fits. When the thermohaline is strong, we cool. When it's weak, the thermohaline, or the MOC, the thermohaline is the Atlantic component, which is probably more dominant. So now there's been an upward trend according to the measurements, but that's questionable. A lot of people are questioning that, just how much long-term warming we've had. But if you go with the average 0.6, 0.7, that's due, to my view, to multi-decadal variations. The 20th century thermohaline in the Atlantic was different than the 19th century, or rather the 19th century was stronger, the 20th century has been weaker. So we have a multi-century scale, multi-decadal scale, and we have year-to-year variations. So I made a prediction of this in 1996. I said to me, because the MOC had picked up in 1995, that we're going to have a new, more cooling. I said the mean global surface temperature in the next 20, 30 years would be driven not by anthropogenic effects, but more like natural cooling from the oceans, driven from salt. For this, I had all my grants cut off. But this is closer to the truth, I think, than what we've seen than what the global models have been telling us. So, my conclusion is the ocean, not CO2 increase, is a primary driver for climate change. CO2 increases are beneficial if they're not going to disrupt the climate, which they're not going to. And climate research must become free of the political domination that is destroyed. And I've been attending these Heartlands. I'm an old guy. I've been around for 60 years. I know a little bit. People say I should have learned much more over that period. But I know something. And you can read about it. Check our Colorado State site here and so on. You can read more. I'll have more coming on this. Thank you.